Welcome back to the course of chemical crystallography. Today we would like to discuss about the basics and applications of powder X-ray diffraction using a presentation, and then in a later stage we will take you to the powder X-ray diffractometer room and show how the sample is prepared and how the diffractometer is used and the data is recorded. So for our clear understanding, I would again like to go back to something which I discussed in the very beginning, that is the sources for powder X-ray diffraction, little bit of Bragg's law which you already know, the crystal structure determination using the powder X-ray diffraction data, and I will introduce you to reed field refinement, but I will not go in much details of reed field refinement in this course. So as you know that electromagnetic radiation to be diffracted by the spacing in the grating should be of the same order of the wavelength. So that is why we use X-rays of very small wavelength, 1 to 2 to 3 angstrom is suitable for X-ray diffraction. So hence X-rays can be used to study the structures because interatomic distances or interplanar distances are in the range of 1 to 2 to 3 angstroms. So what happens, as you know, that the beam of electron falls on a target and is diffracted in all possible directions, and it is the X-rays that are generated. So an accelerating source of electrons are allowed to impinge on a metal target. So immediately it removes one electron from the innermost orbital, and the next level electron jumps down and emits a particular characteristic radiation. So when the electron jumps from the next higher shell, it emits K alpha, and when it jumps from the even higher next higher shell, the second higher shell, it is called the K beta. In general, for all X-ray diffraction purposes, we use this K alpha radiation for any X-ray diffraction applications. As you already know, there are different metal-based sources that are used for X-ray diffraction. Molybdenum, copper, cobalt, iron, chromium, these are different metals. Nowadays we have silver based sources as well, and you can see the wavelengths are varying from 0.71 angstrom to 2.29 angstrom. The most widely used radiation is molybdenum, and it is used for single crystal X-ray diffraction, which you already know. Copper X-ray is used mostly for powder X-ray diffraction purpose because of its larger wavelength. So as you know from Bragg's law that we have the Bragg's law as n lambda equal to 2d sin theta. So we have X-rays falling on the sample and getting diffracted from the bulk of the sample, and the constructive interference only happens when this path difference is equal to the integral multiple of the wavelength. So what we say is Bragg's equation is a negative law. That means if Bragg's equation is not satisfied, then no reflection occurs. But if Bragg's equation is satisfied, a reflection may occur. Why? Because you already have seen there are conditions where there is a systematic absence. So if a particular plane follows, or if a plane becomes systematically absent, that means the diffraction is not happening in if a plane matches the systematic absence conditions, which means that the constructive interference does not take place for that particular plane, and then we do not see the diffraction from that plane. So diffraction is a reinforced coherent scattering, and it is different from reflection. As you know, the reflection occurs from surface, whereas diffraction occurs throughout the bulk. Reflection occurs at any angle. When you shine light on a surface at any angle, reflection occurs. Diffraction takes place only at Bragg angles. Generally, 100% of the intensity may be reflected during a reflection process, but only a small fraction of intensity is diffracted during a diffraction process. So, X-rays can be reflected at very small angle of incidence, that is a different region of X-ray crystallography. So, as you know, we will not spend too much of time on this, that we have Bragg's law, n lambda equal to 2d sin theta, n is an integer and it is the order of reflection. For copper K alpha radiation we use, and suppose the D110 for a particular lattice is 2.2, we can calculate the corresponding lattice parameters and all that using this formula, which is dH scale equal to a by square root of h square plus k square plus l square for cubic systems and so on. What we need to know here is, in powdered X-ray diffraction or in X-ray diffraction, nth order reflection from HKL plane is considered as first order reflection from NH, NK, NL set of planes. So, we can write n lambda equal to 2d sin theta in another way, that lambda equal to 2 d by dH scale by n sin theta, which is nothing but lambda equal to 2d nh nk nl sin theta. So, this is a common setup of the powder X-ray diffractometer or the instrument. What we have is a measuring circle like this, as I have drawn here. At the center of the circle we have a plate which holds the sample. At one end of the circumference of the circle we have the source, that is the X-ray tube, and on the other side of the circle, at the circumference of this measurement circle, we have the detector, and the angle between this direct beam and the diffracted beam is called the 2 theta, as you already know. So, in this X-ray diffractometer, we have three parts: source, sample holder and detector. This sample holder is shown in such a way that it works on the reflection geometry, which is called the Bragg-Brantino geometry. We will come to this soon. This is again a schematic diagram of the diffraction experiment. Here you can see that the X-ray tube is mounted in a vertical fashion and the X-ray beam is coming from left to right, as I am showing here. And then this, I have a specimen holder, that is the sample holder, and it gets diffracted and recorded there. So now it is possible that this specimen is rotated about its own axis, as is shown here as the alpha. So this rotation of sample in front of the beam is done to remove any special orientation effect. This angle of incidence is theta, angle of diffraction is also theta, and the difference between the direct beam and the diffracted beam is nothing but 2 theta. So now this reflection geometry, which is called the Bragg-Brantino geometry, can be used in two different ways. In one case, the X-ray tube is fixed. Both specimen and the receiving slit or the detector moves simultaneously. So suppose if this is the sample, this is the detector, the sample and detector both move like that, keeping the X-ray source fixed at one place. So that is called a theta to theta geometry, because specimen rotates by angle theta when the detector rotates by an angle 2 theta. On the other hand, the Bragg-Brantino theta-theta geometry is something where you have the X-ray tube and the detector moving together keeping the sample fixed in the middle. So if the source is giving beam like that, you have the sample in the middle and the detector is like this. So then when this theta theta geometry is used, both detector and the source goes continuously up. This is the corresponding theta theta geometry, which we also have in our diffractometer, where both the source and the detector goes up during the data collection process. This slide is going to describe the optical alignment of this powder X-ray diffractometer X-ray beam. See, for a powder diffraction, we do not use a circular focused beam, we use a line focused beam where the line is falling on the sample. So now this line can be a divergent beam or can be a parallel beam. So there are two different ways one can use that beam for the experiment. So this schematic diagram shows the cross beam optics, which is a patented technology by Rigaku Corporation. Now it is Rigaku Oxford Diffraction. The BB is Bragg-Brantino and PB means parallel beam geometries are simultaneously mounted and aligned, and they are selectable by a change of slit. So if you have a source and the source has two openings here in the shutter and both the beams come, so once you pass through the first shutter, then you have a Bragg-Brantino slit which allows the divergent beam to fall on the sample and cover the larger area as much as possible of the sample and go back and get diffracted. Whereas in case of parallel beam geometry or parallel beam slit is used, the top beam which was open here is now blocked, and the bottom beam which comes through the lower part of the slit gets reflected from this multi-layer mirror, and the divergent beam, after getting reflected from this, becomes a parallel beam which falls only on a portion of that particular sample and gets diffracted. So this parallel beam geometry is actually useful when you have a very small amount of sample and the rest of the sample plate is empty. So you do not want the sample plate also to diffract. So if you want the beam only to fall on your sample, we just localize the sample in the middle and do this experiment. This is a diffractometer, photograph of a diffractometer of a very old fashion, where the goniometer used to be mounted on the horizontal base. On the right hand side here we have the X-ray tube. The X-ray beam comes like that in the horizontal direction. In front we have a beam stop which stops the direct beam, and on the other end we have a detector which in those days used to be wire-based detector or position-sensitive detectors. So here what happens is the sample is placed in a capillary, and the capillary can be rotated about its axis by about 300 RPM or 100 RPM or whatever, depending on what you want. And then the diffracted beam is actually passing through the sample. So it is called a Debye-Scherrer geometry, not a reflection geometry, it is a transmission geometry. So you have one capillary mounted, you have X-ray beam coming from this side, it is getting transmitted through the sample and getting diffracted on the back, and the detector is recording the diffraction pattern. So this transmission mode geometry is particularly useful for samples which are less absorbing in X-rays, and is also useful when we mount the sample in a capillary. You see, many samples can be moisture sensitive, air sensitive or whatever. So those samples then need to be closed or enclosed in a glass capillary, a special Lindemann glass capillary, and then those capillaries are mounted on this type of capillary rotating stage, and then you do the X-ray diffraction experiment. So, what are different applications of powder X-ray diffraction? The applications range from the detection of how the material is, whether it is a solid or amorphous material. So, we want to know the crystallinity of a substance. One can use it for Bravais lattice identification only. You can use it for lattice parameter determination, identification of known or previously reported materials or phases, identification of different phases or polymorphs or solvates, detection of impurity, structure solution, and rate field refinement as well. We will try to see one of these points one by one. See, as you know that the amorphous materials do not diffract X-rays in any way that as you know that the amorphous samples diffract X-rays and shows a peak like that, which is a very broad hump, and the crystalline materials diffract X-rays following Bragg's law and gives individual peaks. So that indicates that a material will be crystalline if it gives you a set of peaks following Bragg's law, and if it simply gives a hump, one or multiple humps, it means that it is a liquid or an amorphous sample. So when we try to identify the Bravais lattice and unit cell parameters from a given powder X-ray diffraction data, we need to follow a few guidelines or steps. We first select the peaks in the PXRD pattern with minimum threshold. So we do not want to eliminate any very small peak that may be present in the powder X-ray diffraction pattern. Then we try to index these peaks using some standard programs, computer programs, Trior, Digwall, Ito, and all that. Nowadays we have Dash as well for indexing. PDXL also does the indexing of powder diffraction data. So then, based on that, one can identify the lattice type, and based on systematic absence and after indexing, one can try to get the space group as well, but that is very difficult. The first thing is that one has to record a very high quality PXRD data using the instrument available. So to measure a powder X-ray diffraction data, we need to remember a few things. Number one, the sample quality. For a powder diffraction data measurement, the sample must be finely powdered. It should not be with moisture, wet or moisture sensitive, or it should not contain any moisture in it, so that it should be a free flowing powder. Number two, we need to know the range of 2 theta for the sample. So a priori we will not know this number. So what we can do is mount the sample, collect the data very quickly, like about 10 degree per minute or whatever, from 3 to 70 degree 2 theta, and see what is the range of peaks that we are getting for this particular sample. Depending on what range we get, we should choose a specific region. Say for example, we have only peaks from 3 to 50 degree in general for organic or organometallic samples. This range is 3 to 50 degree 2 theta. This is a general common range for organic and organometallic samples, but for different inorganic materials, we may want to go to about 100 degree in 2 theta, because there will be peaks at much higher angle as well. Then we decide the scan speed. Depending on the need of this data, what will be the application of this data, one has to choose the scan speed. A scan speed can be as fast as 20 degree 2 theta per minute to as slow as 0.2 degree in 2 theta per minute. You can imagine that for recording from 3 degree to 50 degree with 20 degree per minute, it takes only about 3 minutes. When it is 0.2 degree per minute, it will take about 300 minutes, which means about 5 hours. So what we are going to do with the data becomes important while choosing this scan speed. What happens when we use a slower scan speed? We can use the step size. So the fourth point is the step size. What is the interval of 2 theta at which we want that data to have 1 point? So normally this step size is about 0.1 degree in 2 theta. This can be reduced to 0.05 degree in 2 theta depending on the need. It can be as low as 0.001 degree in 2 theta, provided the sample is highly diffracting and we would like to use this sample, or we would like to use this data for structure solution and refinement purposes or for Rietveld refinement and so on. We need to choose the step size accordingly. The step size and scan speeds are to be chosen in such a way that it is not too fast or it is not too slow. So suppose if we do a scan speed of 5 degree per minute with a step size of 0.001 degree per minute, for 0.001 degree in 2 theta, that means it is extremely fast for every data point. Whereas if we do the reverse, if we do it like 0.05 degree per minute and 20 degree per minute scan speed, then also it is extremely fast. So depending on the need and requirement, we should choose this scan speed and step size accordingly so that a sufficient amount of time is given for every step to record the diffraction data. This will help us in resolving the peaks which are very close in d value in case of different samples. The point number 4 that one has to remember is sample rotation. A powdered sample is an assembly of a large number of microcrystalline particles, and it may be possible that a large fraction of those microcrystalline particles, when spread on a sample plate, gets aligned in one particular direction due to the mechanical force applied during the spreading process. So if that happens, then some of the peaks which are coming from those pre-aligned crystalline particles will have unusually higher intensity compared to the other peaks, which is called a preferred orientation effect. So to avoid that special orientation effect, one has to rotate the sample about its axis during the data collection. Normally it is done at about 100 to 120 RPM speed. In general, these powder X-ray diffractometers are not equipped with a monochromator. So these peaks that we see are combination of K alpha 1 and K alpha 2. But if you want, you can use a monochromator as well to get only K alpha 1, but in that case the intensity of K alpha 1 reduces drastically. So these are the points one has to remember during a data collection. Often what we see is for organic and pharmaceutical samples, diffraction data often contain very few peaks. See here we have one large peak, but other peaks are extremely small and they are very broad. If you try to enlarge them, you will probably see this peak when enlarged looks like that. This indicates that a large number of D values are hiding in between here and there. It may be a combination of several such peaks. So this becomes a difficult process to get indexing done on this type of samples. It may be the case where it is non-reproducible data due to preferred orientation effect. Once we have recorded a data, we get this type of intensity statistics as shown here. In a different experiment on the same sample, we get different intensity statistics. You see the peak positions are the same, but the intensity statistics or intensity ratios are different. So these different intensity ratios indicate that there is some problem in sample preparation or the sample rotation was not done. As a result, these preferred orientation effects have come up so significantly. So during the process of indexing, and once again we use the condition of Bragg's law in reciprocal space, and all of us now know this particular relation between the 1 by d HKL with the HKL and the reciprocal lattice parameters A star, B star, C star and alpha star, beta star and gamma star. You see, this equation is a cumbersome equation when it is for triclinic, and that is why we need a computer program to solve this equation for a large number of H, K and L with A, B and C as unknowns. What we have knowns are the corresponding D values and the 2 theta values where it is appearing. So here we have unknowns like A, B, C, H, K, L, alpha, beta, gamma. So we have 9 unknown quantities. So we need a large number of D values to be able to solve this simultaneous equation to get the values for A, B, C and then identify each and every peak in the powdered diffractogram with the corresponding Miller indices H, K and L. This becomes easier when we use any cubic sample, which I think have been discussed in one of the lectures where we try to index a powder pattern for a cubic system using a device error method. So, as you know, for indexing you need large number of well-defined peaks. Attempting to index a poor data is not advisable. What do we mean by a poor data? Is nothing but if you have data containing large number of this kind of peaks, or the peaks are very broad, or you have one peak very large and the other peaks are extremely small and disappearing in the background. If you have some such kind of powder data, there is no point in trying to index those diffraction patterns. It is like trying to solve a jigsaw puzzle with half or some pieces missing, because you see, you need to solve this simultaneous equation which contains total 9 unknown quantities and only observed parameters are a set of DHKL. So until and unless you have a large number of well-defined D values, the computer program will not be able to solve these equations and give you correct numbers for A, B, C, alpha, beta, gamma, and then HKL as well. Even in case of some pseudosymmetry, for example, certain lattice parameters may have values that may result in the symmetry of the lattice appearing to be higher symmetry. For example, monoclinic system with beta angle very close to 90 degree, often wrongly indexed as orthorhombic. Unit cell parameters with a monoclinic symmetry but having A equal to C and gamma equal to 120 degree may also lead to, beta equal to 120 degree may also lead to hexagonal lattice. So these things can give wrong information in your indexing software. There may be instrumental errors as well. So a satisfactory solution may not be obtained if there is a 2 theta 0 error greater than about 0.08 degree. So if there is any instrumental error in the system and every peak is deviated by about 0.1 degree, then the indexing software would fail. So for every experiment of powder X-ray diffraction, one should look at this particular peak before measuring the sample. One should use powdered silicon and measure its first peak, which corresponds to 100 reflection that appears at 28.44 degree in 2 theta. So by measuring this standard reflection, we make sure that the diffractometer is well aligned and it is 0 when it goes to 0. A powder diffraction pattern may also show that there are presence of impurities, but when we get a sample, when we try to measure powder X-ray diffraction data on a sample, we do not know whether the sample contains any impurity or not. So in addition to the regular peaks, which may be sharp and well spaced like a real structure, there may be some peaks which might appear from some other impurity present in the sample. So at the beginning, we will not know that the sample is not pure. So in that case, what we would do is we would try to pick up all those peaks that have appeared and then throw them in a computer program to solve those simultaneous equations. But you see, if the peaks are not from same compound, although they are following Bragg's law of diffraction, but the unit cell parameters are not same, so the d values will not match, and as a result the indexing program will completely fail. It will not be able to identify these peaks, not be able to solve the ABC alpha beta gamma. The another case can be such that during the data recording, the sample might change the phase during the data collection itself, which can happen for samples which are sensitive to moisture. During the X-ray diffraction, which may take any time between 10 minutes to 1 hour, during this process, if it absorbs moisture and changes phase, the beginning part of the data will have the patterns from one particular crystal, and the later part of the data will have the hydrated or aquated sample diffraction data. So those peaks we will not be able to identify physically because we don't know that the change has happened. So once we throw those peaks to the throw those peaks to the indexing programs like Tree or EAT or Digwall, they will fail and will not be able to give us any indexing. Here is one classic example of the use of better step size than normal. So when this data was recorded with a step size of 0.02 degree and the counting time of 20 seconds per step, all the peaks that were selected gave us one triclinic lattice like this with volume 416 cubic angstrom, but we saw that the figure of merit values are very small. And what we identified is that for one particular peak, there was no corresponding calculated position. So there is option that you can calculate the peaks based on the indexing as well. So one particular peak did not have the calculated position, or rather the calculated peak position, there was a peak, but there was no real peak in red in that. But then when the same data was recorded with much smaller step size of 0.008 degree into theta with a longer data collection time, 30 seconds per step, what we see is that the figure of merits have improved a lot. These are the parameters that come as outcome of that data indexing software, and it gives an orthonomic unit cell of 4 times volume, and all the peaks that are originally there in red are calculated in blue, and the difference is here. So for that tiny peak which was not there in the original peak is now showing up here. So that peak means that indexing means that the unit cell that we are getting is right, because it then calculates all the peaks that are present in the lattice and it does not calculate any additional peak. Severely overlapping peaks also may result in no indexing at all, which means if the d values are very close for one particular sample, then also the indexing software will fail. If you concentrate on this region, you can see that the peaks around here, peaks around there, and also peaks around there are merging on one on top of the other, and hence the indexing software cannot do justice to this particular pattern. Correct space group determination is the most difficult job here, because as you know, the choice of space group is based on systematic absence conditions. In case of a routine X-ray data, single crystal X-ray data, you have a large number of HKLs. For example, you may have some 1000, 2000, 3000 reflections. So once we go through all those reflections, it becomes easy to identify the systematic absence conditions. But here, the total number of peaks may be 100, at best 150, but then among those 150, we need to look for special reflections like 800 or 0K000L or 80L, HK0 or whatever. All those special reflections which suffer due to systematic absence are very less in number, and then it becomes very difficult to determine the space group from this powder X-ray diffraction data. What one can do is that you can identify the index data using ICSD. Inorganic crystal structure database is maintained by International Center for Diffraction Data. So it actually now maintains both inorganic and organic powder X-ray diffraction data. So if one has access to this ICSD and organic powder structural database, you can use the database, compare the powder pattern that one has generated with the already reported powder X-ray diffraction data, and then one can conclude that okay, I have generated a previously known phase, or I have generated a new phase of that same material. If we know the history of a sample, how the sample was made, then one can identify what kind of impurities that may be present using these databases as well. So, for example, if we have done a solid state reaction by reacting two different oxides at very high temperature and tried to make a new material, if the new material contains some of the starting materials, some of the starting oxides, tiny peaks of those starting materials would appear in the final powder pattern, and one can then identify by comparing the observed pattern with the reported pattern for starting materials, the peaks that are from starting material. So here I am showing one example of identification of polymorphs by powder X-ray diffraction data. As you might know that polymorphs are structural variations of a given compound which was probably crystallized using different solvents, different temperatures, or maybe even different methodologies like solvent evaporation, solvent drop grinding, and so on. Even polymorphs can be generated from same beaker in the same solvent but have two different structures. So polymorphs are structural variation of a single compound that we can think of. So here you can see that a particular compound, fluconazole, we used this for our experiments in the lab. There are 9 different polymorphs of this compound known, where the polymorph 1, 2, this is a monohydrate, polymorph 4, 5, 6, 7, 8 and 9. If you look at their powder diffraction data, you can see the peak positions are all different. Polymorph 1 has the first peak somewhere here, but polymorph 4 has peaks there, polymorph 5 has a first peak here, polymorph 6 has here, 7 here, and all that. And then the maximas are at all different places. So this indicates that a powder X-ray diffraction pattern is very useful in identifying generation of different polymorphs. One can simply compare the powder patterns placed one on top of the other and identify whether they are the same crystalline phase or different. Powder X-ray diffraction patterns can be used to identify different phases. So here what I am trying to show is the follow-up of one experiment. The lowest most one is a pure drug called enrofloxacin. The second one that we have is a co-crystal former, organic acid, fumaric acid, and we tried to mix them in 1:1 ratio and trying to grind them using some solvent, thinking that they will react and form a salt. So after first grinding, what we see is that the peaks of both drug and co-former are simultaneously present. See, these peaks are from drug, these peaks are from co-former, these peaks are from drug. And when we are doing this grinding experiment a few times, what we see that slowly the peaks of the drug is disappearing. See, this is a peak of the drug. That peak has totally disappeared here, there, and that's it. See, these peaks were there, it was slightly there, it is still little bit there, and then new peaks appear here. So this following up of a particular grinding and crystallization experiment is done using a powder diffraction method. So again, the same kind of experiment that was done on a different sample, and what we see here is that this experiment is not going. So even during grinding 1 to 2 to 3 to 4, the peaks of the drug enrofloxacin is not disappearing, this peak remains as it is after several rounds of grinding. So this indicates that the reaction is not going. So one can use powdered X-ray diffraction to see whether a reaction is going or not. Now in this busy slide, I will explain the steps in determination of structure from powdered X-ray diffraction, which I must say that is one of the most difficult tasks to do in X-ray crystallography. But there are research groups who work on these for various samples where one cannot generate the single crystals, or some phases only exist in powder form and it changes its form when recrystallized, and so on. So what is done is that in case of structure solution from powdered X-ray diffraction, the first most important point is to get a very high quality powdered X-ray diffraction data. So normally this powdered X-ray diffraction data is recorded at a synchrotron source with a very high intensity X-ray energy, and as a result the data that you get is highly resolved. The peaks that you get are very sharp, no merging of peaks, so one can identify all the peaks uniquely and then index those peaks. So here the schematic diagram shows the entire process of powder structure solution from powdered X-ray diffraction. So the first point is the preliminary processing, that is to extract the 2 theta values and intensities of all the peaks that are there in the pattern. In this case, we try to collect the data as much as possible, sometimes from 3 degree to 100 degree in 2 theta, even for organic samples, and then we throw all these 2 theta values, that is the D values, to a suitable indexing program and identify all the peaks with the corresponding Miller indices HKL and calculate the lattice parameter A, B and C with alpha, beta, gamma together. We should have a reasonable idea about the density of the sample, which then would allow us to identify how many such molecules are there in the unit cell to give us that particular density. This will identify whether we have Z equal to half structure, Z equal to 1 or Z prime equal to 2. I mean to say that whether in the asymmetric unit I have half molecule, that is Z prime equal to 0.5, it can be Z prime equal to 0.333. If the molecule has a threefold axis, Z prime can be even 0.25. If the molecule is sitting on a 2 by M position, a special position, or Z prime can be equal to 1, 2 and any other higher number as well. So to know what is the value of Z prime, one has to have information about the density of the unit cell, density of the compound, so from that one can guess the unit cell contents. Using the large number of HKLs originating from the data, one has to guess the systematic absences, get the systematic absences and try to determine the space group with the information of Bravais lattice, whether it is monotic primitive or centered lattice or whatever. So once we know the unit cell parameters and the space group, the next step is to do a pattern decomposition. This pattern decomposition also is not very easy. There are a few software that one can use to generate the I-OBS and get the F-OBS for a large number of reflections generated from a very limited number of reflections present in the powdered X-ray diffraction data. So then if this pattern decomposition is successful, there are Pauli methods to do that, and then this pattern decomposition and maybe some other direct space approach, you try to solve the structure. So after getting a larger number of HKLs with the corresponding I observed and calculated structure factor, that is F observed, one can solve using standard methods and get a starting model, that is the starting model of that particular structure. So then one can apply the phases, you can do Fourier and go back and modify the model. So this model to phase, phase to Fourier, Fourier to model, this cycle continues repeatedly till again the R factor is lowered and so on, and we reach a reasonable structure. There is another way that is possible, is that after getting the indexing done, if one can identify if this particular unit cell is matching with a known molecule, and if the known molecule has the same molecular formula with our compound, then one can try to do a method which is called Rietveld refinement and refine the freshly collected powder data on our sample based on the data that is available on a different sample. So suppose if one has a data on a compound AB2O3, for that we know the coordinates of A, B and O, but then somebody has made a compound AB O3 MN2O3 and finds that it has a same lattice parameter as that, it has the same powder diffraction pattern as AB2O3, then one can use the coordinates of A, B and O for the coordinates of M, N and O to start with, and then do a refinement which is called the Rietveld refinement of structure solution, and use this method to elucidate structure of samples which are not known but is known in terms of structural class determined by somebody else. So this Rietveld refinement, I am not going in much details because that is also a different area of research and involves a lot of mathematics and understanding of this refinement. We will end our discussion on powdered X-ray diffraction today with this note that this is the most useful method for structural characterization. One can find out a large number of different physical parameters, identify polymers, identify impurities and solve structures and do Rietveld refinement. I must say that this structure solution from powdered X-ray diffraction is still very difficult even today. So the take home message is powdered X-ray diffraction is used in different capacity for various applications. Bragg's law is always obeyed. Peak positions and relative intensities are of utmost importance. Repeated measurement of the same sample is needed to ensure the accurate peak positions and relative intensities. Knowledge of available or known or reported structure from ICSD is also very important to identify the known phases in the analyte and to detect new or unknown phases. So when we go to the powder diffractometer room, we will demonstrate how a powder sample is prepared and a data is recorded and then interpreted.